then change the guess to T y of P. Okay, so what this one means is you will find your guess, but if your guess, if y of P is the same as one of the fundamental solutions that you found for the homogeneous part, then you have to multiply your guess by T. If y of T satisfy L of T y of P is equal to 0 as well, then change the guess to T squared. So if the T of y of P also satisfies or is one of the solutions, then you have to get the guess to be T squared y sub P. Okay. So this one mostly happens when we have the repeated roots. Then the next one says that find the undetermined coefficient k in the function. Okay, so in the guess, we will have some undetermined coefficients, some k. And he says that you should find your k using the equation L of y is equal to f, where y is y sub p or t sub p or t squared sub p. So this is the table. So the undetermined coefficient method, this is the table. The list of source f and then solution to the equation L of y is equal to f. We did this one too in vector algebra and differential equation. Do you remember that? Am I online? Did you remember that one too? In vector algebra and differential equations.
Small.
Hello.
Hello, madam.
Gloria, you don't remember?
No.
Okay, so let's continue. So as I said, you look at the right-hand side. If the right-hand side is an exponential function, it is ke to the power 80. So what I'm trying to say is, if the function is written as y prime prime plus a1 y prime plus a naught y is equal to e to the power 80. If this side is an exponential function, then your guess function is ke to the power 80. This is your guess function. The solution y sub p will be this. Now, if that side is a polynomial, so if this side, so if the function here is not exponential but a polynomial function, k t to the power n plus k2, so kn minus 1, 2 to the power n minus 1, and so on, then your guess will be k tn, k sub mtm, and so on. Now, if it is a trig function, so if this side, is a trig function, maybe k cos t, maybe plus sine t, or only cos, or only sine t, then your guess will be, so if it's a combination of the two or one of them, then your guess will be k1 cos bt plus k2 sine bt. Now, if it's a combination of polynomial times exponential, then your guess will also be combination of exponential trig polynomial times exponential. If it's a combination if it's a product of trig times trig and then exponential, then your guess will also be trig and exponential. If it is polynomial times trig, then the guess will be like this. This is the undetermined coefficient method. It is a set of simple rules to find a particular solution y sub p of a non-homogeneous equation L of y sub p is equal to f, in the case that the source function f is one of the entries in the table. There are a few formula in particular cases and then a few generalization of the whole method. We discuss them after a few examples. Okay, so let's look at it. It says that find all the solutions to the homogeneous equation y prime prime plus 3y prime minus 4y is equal to 3y to e to the power 2. So what we do is we have to first of all find a solution to the homogeneous part. Of course, we know how to find solution to homogeneous parts. So to the homogeneous, we have to get our characteristic polynomial. So our characteristic polynomial will be r squared minus 3r minus 4. We solve for this and we're going to get our solution to be 4, root to be 4, and then minus 1. So this means that my solution will be e to the power 4t and then e to the power minus t. So it says that find fundamental solutions of y minus and y plus to the homogeneous equation thus. Since the homogeneous equation has constant coefficient, we have the characteristic equation. So we know that the solution will be C1 e to the power 4t plus C2 e to the power minus 4t. Now the next thing is, it says that we should compare. We have to look at what we have here. What we have here, it is 3e to the power 2t. The 2 is not a root of the homogeneous parts. It is not a root, so we are fine. So we have 3e to the power 2t. So we go to the table. It says that if the source function is ke to the power 3t, then our solution, our guess should be ke to the power 3t, ke to the power 80. So here it is 3e to the power 2t. So our guess will be ke to the power 2t. The constant k is the undetermined coefficient we must find. Okay, so it says that our guess function or solution is ke to the power 2t, and then e to the power 2t is no solution. It's not one of these two. Okay, so it's not solution of the homogeneous equation. We do not need to modify our guess. So we are told that it's not a solution, so we don't need to modify our guess. But let's assume if this one were to be 4t, then it means I have to multiply my guess by t. So that's what it says. Recall L of y is equal to 0 if and only if there is a C1, C2 such that my y of t is equal to that. Okay. So let's continue. Introduce y sub p into L of y sub p is equal to 0 and find for k. Okay. So that's what I do. After getting my guess, I have to find my first derivative, second derivative, and substitute them into the original function. So I find the first derivative. I have k. The function is ke to the power 2t. What will be the first derivative? Please, what will be the first derivative for this?
But for which one? It will be
K,
2k e to the power 2t.
and what about the second derivative?
4k.
4K.
4k to
To the power. Okay, so I have to find my 4k, which is the same as 2 squared. Then minus, remember this is 3. So I multiply my 3. You said that the first differential will be 2k e to the power 2t. So 2k times the 3 will give me 6k e to the power t. So that's what we have here. So you're going to get 6k e to the power 2t. And then here, the function here is 4. So I'm going to get 4k, this is equal to 3. Okay, so let me just write. So we know how to find the homogeneous parts. So the non-homogeneous part, as I said, our guess will be y is equal to, so it's y2 is equal to k e to the power 2t. So I find y first derivative, and you said it's going to be 2k e to the power 2t. And then my second derivative, which will be equal to 4k e to the power 2t. So I go back and write this function. I'm going to get 4k e to the power 2t minus 3 times 2k e to the power 2t plus 4 times my y is 4k e to the power 2t. And this is equal to 3 e to the power 2t. So that is it. So when I expand, I'm going to get 4k e to the power 2t minus 6k e to the power 2t, then plus 4k e to the power 2t, which is equal to 3 is. Please solve for me. So it's the same thing. This is 4. So I'm going to get minus 6k e to the power 2t is equal to 2et. Even this can go. So I have negative 6k is equal to 3. Then my k will be minus 1. K is what?
Negative half.
Negative half. So it means that my solution yp is equal to minus 1 over 2 e to the power 2t. Then the total, the general solution, it's a solution to the homogeneous part plus the solution to the non-homogeneous part. So therefore, my solution y will be equal to, remember the homogeneous part, I had C1 e to the power 4t plus C2 e to the power minus t. So that is the solution to the homogeneous part. And the non-homogeneous part minus 1 over 2 e to the power 2t. That is all. Okay, so it's true. So I have C1 e to the power 4t plus C2 e to the power minus half minus t, then minus 1 over 2 e to the power 2t. So that's how to go up. Please, any question?
Hello, madam. Madam.
Yes.
Please, the minus is there. Can you clarify it?
The minus t.
6.
The minus.
Minus 6.
The minus 6. This one.
Yes. From your solution, after
From
you
my
have substituted the.
so my
Yes.
solution is the original function. The original function was y prime prime minus 3y prime plus 4y is equal to 3e to t. So do you get it now? And then the first derivative is 2k. So that's the reason why it came 6.
Okay. Thank you.
Okay. So there's another one here. You have y prime prime minus 3y prime minus 4y is equal to 3e to the power 40. So this is the homogeneous part is what we just did. So when you solve, we're going to get this one, going to get e to the power 40 and then e to the power minus t. Here is e to the power 40. So our guess cannot be k e to the power 40 because e to the power 40 is a solution to the homogeneous parts. I shall bring Adama. Yeah, close down. Okay. So the source function is f of t. Where is Insha? Go ahead. So the source function is f of t is equal to 3e to the power 40. So the table says that we need to guess y of t to be 4e to the power 40. However, this function y of t is a solution of the homogeneous parts because y p is equal to ky plus, and this is equal to 0. So it means that this cannot be our guess. So from the beginning introduction part, it says that if it's a solution, then we have to multiply it by t. So our guess will now be kt e to the power 40. You can see that this is not a solution. So here our y prime is, our y sub t is, kt e to the power 40. So here I have to find my first differential, second differential, and substitute them into the equation and simplify. Are you okay? Please, are you okay?
Yes, madam.
Okay. So this new guess is not solution of the solution homogeneous. So we proceed to compute the constants. We introduce the guess into the, so we find first derivative, second derivative, substitute them into the function, simplify, and then solve for our k. So our k will be 3/5. So that means that my solution will be 3/5t e to the power 40. So I combined everything and the solution will be this. C1 e to the power 40 plus C2 e to the power minus t plus 3/5t e to the power 40. Now there's another one. So the same homogeneous part, but here the other part is 2 sine t. Okay. So we know that when you solve the homogeneous part, you are going to get so it's the same homogeneous part, and the root will be +4 and -1. But this one, this is not a solution. So we go to the table. And when you go to the table, it says that when I have either cos or sine alone, then my guess will be k1 cos bt plus k2 sine bt. So I mentioned that. So here it says that if we write this function as this with f equal to the, then the operator is the same as the, so the solution of the homogeneous part is the same as this. Since the source function is f of t is equal to 2t, the table says that we need to choose the function y of p to be k cos t plus k2 sine t. So this function y of p is not solution to the homogeneous. So we look for our constant k1 and k2 using the equation. So here, that's my guess. I have to find my first derivative, second derivative, and substitute them into the original function and find my k1 and k2. So I find my first derivative. This is my first derivative. This is my second derivative. I substitute them into the original function. So my second derivative minus 3 times my first derivative minus 4 times my guess is equal to 2 sine t. So I take my time to simplify everything, and I'm going to get this. It says that this holds for all t in R. In particular, it must hold for t is equal to pi on 2. And for t equal to 0. So please, let's solve. We want to solve for this. Okay. So when t is equal to 0, when t is equal to 0, what do I get for this? When t equal to 0, I'm going to get, please, when t equal to 0, what will I get?
Madam, please, which one, please?
Please, I have to solve for this. And to solve for this, I'm choosing, you know that my t, this is a trig function. So I can choose 90, 0, or whatever. And you will see that some of them will give you the same thing. So I'm considering 90 and then 0. So when t equal to 0, I know that cos 0 is, what is cos 0?
It's 0.
Cos 0?
Because 0 is 1,
Madam,
sorry.
1.
Sorry. 1.
So when t equal to 0, this one will be minus 5k1 minus 3k2 times 1 plus, and then my sine 0 will go to 0. This will also go to 0. So I'm going to get one of the solutions to be minus 5k minus 3k2 equal to 0. Now when t equal to pi on 2, which is 90, this side will go to 0, and this side will not go to 0. So I'm going to get two solutions. I'm going to get this equal to 2 and equal to 0. And it will help me to solve for K1 and then K2. So my K1, will be 3 over 17, and then my K2 will be minus 5 over 17. Please, you can just use pi on 2 and then t equal to pi on 2 and t equal to 0. Substitute them here and you're going to get this, please. You can use other values, maybe 180, but you're going to get the same thing. So the particular solution to the homogeneous equation is, so this will be for the non-homogeneous part. So I have 1 over 17. Both of them have over 17. I have 1 over 17. I have 3 cos t minus, so minus 5 sin t. So the general solution, everything combined, will be the non-homogeneous parts plus the non-homogeneous parts. Are you okay? Hello?
Yes, go.
Hello, madam.
Yes.
We are there.
You are there. Okay, let's continue. Example 2.5.4, we provide few more examples of non-homogeneous equation and the appropriate guess. So these are also non-homogeneous equations, and these are the appropriate guesses. So this one, this will be the appropriate guess. This one, this will be the appropriate guess, and so on. So this one is a combination of exponential and then trig. And we know that when you have exponential and trig, the guess will be, the trig will be K1 cos t plus K2 sin t, and then the exponential will be e to the power 2t. Since we have K1, K2, you don't have to bring K again. And this one I have, this is a polynomial, t to the power 2 is a polynomial function. So for polynomial function, it will be K2 t to the power. Okay, so please, to the guess for the polynomial to the power or the degree of the polynomial also counts. If it is to the power 2, then I have to get K2 t to the power 2 plus K1 t plus K naught. If there is no squared here, if it's just t, then I'm going to get K1 t plus K naught. If it's I have to the power 3, then I'm going to get k to the power 3 t to the power 3 plus K2 t to the power 2 plus K1 t plus that. Please, did you get it?
Yes, though.
Okay. So you have to look at the power, the degree here. So this one is a combination of polynomial and then exponential.
But please, in exams, when they give you such a question, would they give you the guess as a guide to so that you follow and solve the
I don't
question?
think so. I don't think so. So please just master it. It's not that difficult. Please.
Oh, okay, though. Thank you.
You're welcome. So here is exponential and then a polynomial, but the e to the power 4 is a solution to the homogeneous parts. So it means that I'm going to get the polynomial. Then because this is a solution, I have to multiply. So I have t e to the power 40. So please take note of that. And then this one too is 3t sin t. So the t is a polynomial. As I said, the power here is 1. So it will be K1t plus K naught before you write the one for the trig. Oh. Please, you can take your time to look at this remark. It says that find all solutions to the homogeneous equation thus. Non-homogeneous equation thus. So this one, I have exponential plus my trig. So I have to find the solution. I know the solution to this. This is the roots I have 4 and minus 1. But my guess is this. But this one, we don't have this one in the table. In the table, we have products. So we don't have the sum. So F1 is equal to 3 e to the power 2, and F2 is 2 sine t. So we look for a particular solution of the form. So this one, I have to look for sum as well. So I have to find, this one will be, it is 3 e to the power 2t. So my guess will be k. My guess will be k e to the power 2t. And then this one is 2 sine t. So my guess will be k1 cos t plus k2 sine t. Okay, so that's what I have to do. Okay, so this one we have chosen this example because we have solved each one of these before in example this. So we found the solution. Okay, so it means that I have to find the k, the one for this I solve for my k, then I come to here the second one, then I solve for my k1 and k2. So that's what I've done. We solved for the first one. The first one we were given that is this example with the example with the b part to be 3 e to the power 2t, and when we solved, we had our k to be 1/2. So that is the solution. And this one we have been given this one already, and when we solved, we have 1/17 3 cos t minus 5 that. So the solution will be the combination of the two. That is for the right hand side. So everything combined, I'll have the homogeneous part, then the non-homogeneous part all combined. That is the solution. Any question? Because we are done with the method of undetermined coefficients. We want to look at the variation of parameters. But any question before we move on to that? Hello? Hello, am I online?
Yes, madam, we are online.
Are you okay?
Yeah, okay.
Yes, madam.
So you have to practice. So the next thing is we want to look at the method of variation of parameters. This method provides a second way to find a particular solution y sub p to a non-homogeneous equation L of y is equal to f. We summarize this method in formula to compute y sub p in terms of any pair of fundamental solutions to the homogeneous equation L of y is equal to 0. The variation of parameter method works with second order linear equation having variable coefficients and continuous but otherwise arbitrary sources. When the source function of a non-homogeneous equation is simple enough to appear in the table, the undetermined coefficient method is a quick way to find a particular solution to the equation. So what we are saying is, if we have a second order polynomial, second order ODE with constant coefficient, and you can get the solution from the source from that table, then that is a quick way of finding a particular solution. But if you cannot get it from there, then maybe you can use the variation of parameter. It says that when the source is more complicated, one usually turns to the variation of parameter method with its more involved formula for a particular solution. So that's the variation of parameter. It says that a particular solution to the equation L of y is equal to f, with L of y is equal to, so by L of y is equal to a second order differential equation. This one is the homogeneous part, where A1, A0, F are continuous function and is given by L of p is equal to y1, mu u1, y1 plus u2, y2. So this is my particular solution, where y1, y2 are fundamental solution of the homogeneous part this, and the function this are defined by this. Okay, so here we are saying this is the formula. It says that you find the solution to the homogeneous part, and to find the solution to the non-homogeneous part, which is written as this, you have to find So you will find your y1 and y2. Then you have to find your u1 and your u2. But the u1 is given as this formula. u1 is equal to integral minus y2 f divided by w of y1, y2. Okay. And then my u2 is integral y1 f divided by w of y1, y2. So that's how to do it. So my y1, y2 is the Wronskian of y1 and y2. You know how to find the Wronskian. The proof is a generalization of reduction order. Recall that the reduction order is a way to find a second solution y2 of a homogeneous equation if you already know one solution. One writes y2 to be u y1 and the original equation L of y2 is equal to 0 provides an equation for u. This equation for u is simpler than the original equation for y2 because the function y1 satisfies this. Please, the proof, you can look at it. You can take your time to look at it. You just follow that. But we'll just solve an example. Please, you can take your time to look at the proof, how to get the proof of your U1 and then your U2. Please, the proof is here. But we want to look at an example. It says that find the general solution of the non-homogeneous equation thus. So we have to find the homogeneous parts. So homogeneous parts, we know that you have to get the characteristic polynomial and the solution you're going to get 3 and 2, the roots. So your solution will be y1 is equal to e to the power 3t, and then the other one will be e to the power 2t. Okay. And then we know that to find the particular, the y sub p, it is u1 times y1 plus u2. So it is u1 times y1 plus u2 times y2. We have found our u1 and then y2. We have found them. I have to find here u1 and then u2. And u1 and u2 are given by this. So negative y2 over the Wronskian times f over the Wronskian, and then y1 times f over the Wronskian. Okay, so we have to find them. So it means that we'll need the Wronskian. So my Wronskian, we know how to find the Wronskian. Wronskian is given us from last week. We know that our Wronskian is, somebody will give us the Wronskian. How do we get the Wronskian?
Madam, why
So
you
W is equal
determinant?
to
Yeah.
of
Y1, Y1, and then Y2.
y2.
Yes. Then you find the derivative of Y1 and
So
derivative of
y1
Y.
prime,
Yes.
y2 prime.
Yes. Then you
So
find
that
it
is
determinant. Yes.
okay. So this one is going to be so
Y1. Okay.
e to the power 3t and then e to the power 2t. So let's find the differential of this. Differential of this will give me
3 e to the power 3t.
and this one will give me
But I please, this one is for e to the power 2t or what, please? Okay. Yeah, 2t, please.
so please let's find the determinants. 2 e to the power 3t e to the power 2t and then minus 3 e to the power 2t to the power 3t. Please, what do I get?
Negative e raised to the power 5t.
5t. So that is my Wronskian. Okay, so the Wronskian is negative e to the power 5t. So I have to find my u1 and then my u2. So my u1 is equal to negative y2f over Wronskian. Is, and then this is equal to that. So the equation for u1 is given us the u1 we have to, so my u1 prime is equal to the y2 is e to the power 2t, and then my f is 2e to the power t, and then my Wronskian, where's my f? Please, my f is here. This is my f. This is my f. Is the b of x. So it's going to be minus e to the power 2t times my f, all divided by my Wronskian. Okay, but my Wronskian is negative e to the power 5t, then I'm making it negative 5t. And this, when I simplify, I'm going to get 2 e to the power minus 2t. Remember, I want to find u, not u prime. So my u is integral. So I integrate this, I integrate this. Then integral of this will give me minus e to the power minus 2t. The same thing for the u2. u2 is, the u2 prime is this, but u2 means that I have to integrate. So first I will write the formula as e to the power, so my y1 is e to the power 2t, my f is 2 e to the power t, and then my Wronskian is this. I simplify, I'm going to get minus 2 e to the power minus t. Then I have to find my u, I integrate, and my u is 2 e to the power minus t. That is it. So the solution I know is u1 y1 plus u2 y2. So my u1 is minus e to the power 2t minus 2t e to the power 2t plus, then I have my u2. This is 2e to the power minus t e to the power 2t. You just take your time to simplify and you will see that you're going to get e to the power t. So that is my y of p. So the general solution will be the homogeneous part, which is c1 e to the power 3t plus c2 e to the power, this is 3t plus c2 e to the power 2t, all plus my y sub t, which is e to the power t. So that's how to go about the method of variation of parameters. Please, any question? Any question? Are you okay? Okay. So there's another one here. Want to find a particular solution to the differential equation. This, you can see that this is with variable coefficients, and we know how to solve this. Okay. So that's the homogeneous part. So our candidate is y to the power r. So it is y is equal to t to the power r. You have to find the first derivative, second derivative, we solve, and then it is saying that when we solve, we're going to get y1 to be t squared, and then y2 to be 1 over t. So please, you take your time to solve this. This equal to 0. So these are the solutions to the homogeneous parts. Okay, so even given in the question. We first rewrite the homogeneous equation above in the form given in theory this. Okay, so we write it in this form. So in this form, I have to divide through by t squared. So I'm going to get y prime prime minus 2 over t squared y is equal to 3 minus 1 over t squared. So my f is 3 minus 1 over t squared. So please, anytime you are given this, you have to write it in this form. Then after that, I have my solutions, this and this. So I have to find my raw skin, as you said. Okay. So I find my raw skin. So my raw skin, they are saying when I take my time to compute my raw skin, it's going to be like this. And my raw skin will be -3. Then I have to find my U1 and U2. So my U1 is 1 over T, 1 over T, which is my Y1. So I have my, okay, so U1 is Y2 times F. So I have my negative Y2 times my F, all divided by my raw skin. My raw skin is -3. So I just play around it. I'm going to get this. Then I integrate. So when I integrate, I'm going to get ln T plus 1 over 6 T to the power -2. Then U22 will give me my T1, my Y1, sorry, my Y1 times the F, that is the other side, the B of X, then all divided by raw skin. So I take my time, I simplify, then after that I integrate to get my U. So my U is -1 over 3 T cubed plus 1 over 3 T. So I combine the two. This, oh no, so the function y of p is u1 times y1 and then u2 times y2. So my u1 is like this, my y1 is this plus my u2 is this, and then my y2 is this. I simplify and I'm going to get this. You take your time to see. Right. I have a simple expression for solution of homogeneous equation above is given by this. Okay, so what we are saying is we can simplify this to get this. Take your time to simplify. So that is for my y of p. So my general solution will be the general solution for the homogeneous part. So we're going to t to the power 2 plus 1 over t, or plus t squared ln t plus 1 over t. So that is my whole solution. This one is for just the particular, but the so general solution will be this plus this, then plus the solution we just got. Please, any question? Am I still online?
Yes, though.
Yes, madam.
You're online.
How is it going? Is it okay?
We can't complain, madam.
Oh, but Gloria, do you have to complain? Just what you just need a formula for U1 and U2. And you know how to find raw skin. You can multiply. After getting it, you just integrate. Then you multiply by your F1 and F, and then U1 by Y1, and then U2 by Y2. That, and then you add the two. That will be the so the Y sub P. Then you simplify. You get your Y sub P. You go and add it to the general solution for the homogeneous parts. Gloria, this one, do you have to complain?
No, madam.
So if you want to complain, you can complain. Gloria. So we have been equipped with skills to find particular solutions to non-homogeneous differential equations using undetermined coefficients and variation of parameters, especially when the differential equation contains variable coefficients. We've done that. Yes. Is it true? Is it true? We now know how to
Yes, sir.
use
Yes, madam.
coefficients and variation of parameters to solve. So we are done with lesson 2. Last one, last is lesson. So this lesson 2, right? Last one is lesson 3. And then in the lesson 3, I have only one thing over there. That is a series solutions. Series solutions. Series solutions. I'm continuing. Oh. Can I continue?
Yes, madam. Today we are not taking supper.
Let's finish and then go and take it at 5. Because if we break for how many minutes? Or we can go and take supper and come back. Or but
It's
some of
okay,
you,
we continue. Let's finish, madam.
it's only me and then Madam Gloria. What about the rest? Should we finish and go?
Yes, madam. Please let's finish and go.
Okay, so let me look at this one. How many slides? Oh, just 15. Okay, so let's continue. Series solutions of differential equations. So we just looked at some solutions, but we have other solutions of differential equations, and we call them the series solutions. Before we delve into finding series solutions to differential equation, we need to determine when we can derive series solutions to differential equations. Let's begin with the equation P of x y prime prime plus Q of x y prime plus Q R of x y equal to 0. We have dealt with differential equation involving constant coefficients so far. By this time, we will really deal with non-constant coefficients. Thus, with series solution, we can now have non-constant coefficient differential equations. Now, we say that S is equal to S naught is an ordinary point if and only if provided both Q of x over Q of s and R of s over Q of s are analytic at S equal to S naught. So we want to look at the points, the solution. We know that when we have a function, we last MAT101, 102, we looked at critical points. So the critical points, or which some will call it equilibrium points or phase points, we are looking at that point, the point where S is equal to S naught. So now, if we have that point, we want to find out if that point that we have is ordinary point. And we are saying that if that point is ordinary, then it means that my P of S over Q of S and R of S over P of S is supposed to be analytic. Please, we will look at what we mean by analytic. Okay. That is to say that these two quantities have Taylor series around S equal to S naught. We are going to be only dealing with coefficients that are polynomial, so this will be equivalent to saying that P of S naught is not equal to 0 for most of the problems. If a point is not an ordinary point, we call it a singular point. Okay, so we are saying that if it is not an ordinary point, then we call it a singular point. And we are saying that if it's an ordinary point, then my P of S, my Q of S over P of S, and then R of S over Q of S should be analytic. So if it is not an ordinary point, then it is a singular point. The basic idea here is to find a series solution to a differential equation. Is to assume that we can write the solution as a power series in the form y of s is equal to summing from n equal to 0 to infinity a sub n into x minus s naught to the power n, and then try to determine what the a n needs to be. Okay, so here we want to look at the power series solution. So the first example, the examples that we've done so far, we've looked at exponential solutions, but here we want to look at power series solutions. We will only be able to do this if the point x is equal to s naught is an ordinary point. We will usually say that 1.0.2 is a series solution around s equal to s naught. So we are saying that we can find the series solution if x equal to s naught is an ordinary point. And when we say that it's ordinary point, then it means that it Q over P of X and then R over P of X is supposed to be analytic. If they're analytic, it means that they're ordinary points. Hey, please excuse me. Ishra! Darika! Please come. Let's start with a very basic example of this. In fact, it will be so basic that we will have constant coefficient. This will allow us to check that we get the correct solution. So determine a series solution for the following differential equation. Y prime plus y is equal to 0. About s is equal to x naught. Okay, so we are told that to get the series solution, we have to prove that the point s is equal to s naught is analytic. Notice that in this case, my P of S is equal to 1. Please, we are comparing it with this equation. P of S, Q of S, R of S. So my P of S is 1. My Q of S is 0. And then my R of S is 1. So notice that in this case, P of S is equal to 1. And so every point is an ordinary point. Ordinary points, when we talk about ordinary points, it means that we're going to get a finite value for my P of S, my Q of S over my Q of S over P of S. Here, my Q of S is 0, so 0 over 1 is 0, and it's a value. And then my R of S is also 1, so 1 over 1 is also a finite value. So it means that that point is an ordinary point. When you find the limit as s approaches 0 of that point, it's to give you a finite number. So this one, we're going to get a finite number. So it means that it's an ordinary point. So we'll be looking for a solution in the form like this. So here is the same thing, the same approach as we used to do. So here our y is summing from n equal to 0 to infinity a(n) s minus s naught all to the power n. This is our guess solution. And we know that anytime we have a guess solution, we have to find our first differential, second differential, and then substitute them into the function. So here, if this is my solution, I have to find my first differential. My first differential will be n, a to the power n, a sub n, x to the power n minus 1. So we are summing from n equal to 1 to infinity because this is starting from, looking at this, we should start from n, from 1. And then the second derivative will give me n into n minus 1. I hope you can find the first and second derivative. Given this function, you should be able to find the first and second derivative with respect to x. I hope you can find that. My people.
Mama, please come again.
Can you find the first derivative for this with respect to x? You should be able to do that. So it will be, you just drop this n here, then an into bracket n minus n naught to the power n minus 1. So that would be the first derivative. Okay, so we are told that x1 is equal to 0. So x not equal to 0. So here this is 0. So the function will be summing from n equal to 0 to infinity a sub n times x to the power n. So when you find the first derivative, you're going to get this. Second derivative will give you this. Then we can start this at n equal to 0. So here we are starting n from 1. Here we're starting n from 2 because of this. So we can start this at n equal to 0 if we need to. However, it's almost always best to start them where we have here. It is, if it turns out that it would have been easier to start them at n equal to 0, we can easily fix that up when the time comes around and put this into our differential equation. So we substituting our first differential and second differential into the equation. Please, this is the equation. We have the first, second differential here. We have the function. Okay, so when you substitute them, we're going to get the first differential, second differential here, plus there is no first differential, so we will not, that one, we don't need it. So we need the original function equal to 0. Since this is starting from 0, it will be best if this one to start from 0. So if this one starts from 0, it means that there should be a kind of shifting. So to start from 0 means that I have to add 2 here. When I add 2 here, 2 here will go with the negative 2, then this will be positive. Then I'll add 2 here. When I add, which will please, I'm sorry. So as I was saying, want to shift. So shifting means that we want this one to, we'll add 2, 2, 2, and then this one is like n. And this one, n equal to 2, is the same as n minus 2. So if I write it as n minus 2 plus 2, it will be n equal to 0. So this one too will shift. So when I shift it, this side will be summing from n equal to 0 to infinity. Then I have n plus 2, n minus 1 plus n plus 1. Then this will be a n plus 2, because I'm adding 2 to all the n's. And this one will be n x n minus 2 plus 2. So this will be x n. Then plus this one will be the same thing, equal to 0. Okay. Then I have x to the power n here, x to the power n here. So I can bring that one out, x to the power n, and this side will be left with. So I have summing from n equal to 0 to infinity. It is common here, it is common here. I'll bring that one 2 out. And this will be n to plus 1, have n plus 1, and then a n plus 2 for this side, and this side will be a sub n equal to 0. And then from the 0 product rule, this time this equal to 0 means that if this is not equal to 0, then this is equal to 0. So I'm going to get n plus 2, n plus 1, a n plus 2 plus a sub n equal to 0. So n equal to 0. Then I want to make a n plus 2 the subject. So I have a n plus 2, and this is equal to minus a n over n plus 2 n plus 1. And we are saying that we use this to obtain the recurrence relation and find a series solution to the differential equation with the values of AS. So please, thus we have AN plus that equal to that. And then we want to look at when n equal to 0, n equal to 1, n equal to 2, and so on. So when n equal to 0, it means that the side will be a0 plus 2, which is a2. And this will be minus a sub 0 divided by, so 0, 0 will give me 2 times 1. So that's what I have here. Now, when n equal to 1, it means that I'm going to get a sub 3. Please, are you with me?
Yes, ma'am.
So this is a sub 3, which is the same as, so n is 1, so I have a sub 1. So this one will be minus a sub 1 divided by, this is 1 plus 2, which is 3, and then 1 plus 1, which is 2. I have it like that. Then when n equal to 2, I'm going to get a sub 4, which is equal to, so a sub 2 divided by 2 plus 2 is 4 times 2 plus 1, which is 3. But remember from the top here, I have an expression for a subscript 2. A subscript 2 is minus a sub naught divided by 2 times 3. So in place of a naught, I will substitute this whole function. And this is going to be, so negative, negative, I'm going to get positive. So I have a naught divided by 4 times 3 times 2 times 1. When n equal to, so please, we are just substituting values. So we have this expression. The thing doesn't want to open on. Okay, so we have this expression and we are just taking different values of a. So I have of n, so I have n equal to 2, n equal to 4, n equal to 1, okay, n equal to 0, n equal to 2, n equal to 1, n equal to 3. We can see that when n equal to 0, I have a2, when n equal to 2, I have a4. When n equal to 1, I have a3. When n equals to 3, I have a2. Okay, so my a5 will be, when n equal to 3 is a3 plus 2, which is 5. And this will be minus a sub 3 divided by 3 plus 2 is 5. And then 3 plus 1 is 4. So I have 5 and then 4. But I have an expression for a sub 3. I hope you are following. So in place of a sub 3, I will just substitute this. And this will be a1 divided by 5, 4, 3, 2. You will see that when n equal to 4, when n equal to 4, I'm going to get a sub be sub 4 divided, and I'll have my this. I can come and substitute the expression for a5, a4, and in that I'm going to get a script 0 divided by 6, 4, 2, and n equal to 5, 2. That will be a7, and a sub 7 is sub and expression. So when you take your time, see that be a pattern or pattern for all the one a5, a5, a7, they will all have as the numerator, and the rest. Why, if it is 7, you 7, 6, 5, 4, 2. If it is you have 8, still have 8, 7, and so on. The other or it's first one negative, third one will on the one. You see that negative. That's all of what's in. So you
Madam, your
have
screen is not
when
showing.
it's at nothing as a I'm staring. So please check your network. Then, so it's up. You take your there will be a pattern for all things and then a pattern for this. So the even I said this is for X, this is for that pattern. We see that all of them have a note and by is as K. So for the even case, you get two and it's all two my case as uh, okay. So the minus and the no A K and so on. So I just two, and then this is one. It's going to when n is two, then this and this four. So to get four.
Madam, you are
No
not able
four.
to see anything.
Four.
Madam, please, your network.
Able to see.
Nothing is showing. No.
Is it okay? Hello.
Madam, please, we didn't hear anything, no, and we didn't see anything too. Your network went off. The screen you
Can
were
you
not showing. Not,
I know. Can you see now?
please, no.
Now.
Please, no.
Hello.
Yes, it has come now.
Okay, it has come now. Okay, so as I was saying, I said that the even ones can be written as A2K, and then you have minus 1K and A naught divided by 2K factorial, where K is 1, 2, 3. So all the even ones will have the numerator to be A naughts. And then the odd ones, odd, we know that odd numbers can be written as 2K plus 1. Okay. So we'll have that one to have minus 1 to the power K, and all the odd ones will have the numerator to be A sub 1. So I have A sub 1 divided by the 2K plus 1 factorial. So you see that if it is 7, it is 7, 6, 5, 4, 3, 2, and so on. So that one can be written like this. Then K is equal to 1, 2, and so on. Now that we've got formulas for ANs, let us get a solution. The first thing that we will do is to write out the solution with a couple of ANs plugged in. Okay, so we come here. We know that our solution is summing from n equal to 0 to infinity AN xn. So when I expand this one, This is when n equal to 0, I'm going to get a naught. When n equal to 1, I'm going to get a1 times 1 x to the power 1. So that when s is equal to 2, when n is equal to 2, I'm going to get this. Then up to where I'll be writing a2k's. This is for the even ones, and then a2k plus 1 x to the power 2k plus 1. This is for the odd ones. Okay. So I have a naught plus a1s minus, I have an expression for a3. A2, sorry, A2. The expression for A2 is already here. So this is the expression for A2. I have expression for A3. I have expression for A4, A5, and so on. So I will have the expression for A2, A3. Then I will write the expression for the even one. The even one I said is minus 1 to the power k a naught divided by 2 factorial s to the power 2k plus, then minus 1 to the power k a1 over 2k plus 1 factorial for the odd ones. Okay. So the next step is to group all the ones with a naught and all the ones with a1. So the next step is to collect all the terms with the same coefficients in them, and then factor out that coefficient. So I have a1 here, sorry, a naught here, and then a naught here. So I put them together. I have a naught out, and this one will be left with 1. This will be left with x2 minus s squared over 2 factorial. Dot up to, so I have a1 here. So I factorize it out, and I have minus 1 to the power k s to the power 2k over 2 factorial. So that is for the even ones plus all the evens, and then I come to the odd one. So I have plus a1, that one is a1, x, that will be left with x, then minus a1, so this a1, my a1 is out already, so I have s to the power 3 divided by 3 factorial, then plus I come to the odd one, which is minus 1 to the power k. My a1 is out already, so I have x2k plus 1 divided by 2k plus 1 factorial. So that is that. Then when I want to write this in summation form, the whole of this is a1 summing from k equal to 1 to infinity. This whole thing can be written as, I'll write the expression for the odd one, minus 1k s to the power 2k over 2k factorial. This is for the even one, plus the odd one is a1 summing from k equal to 0 to infinity, minus 1 to the power k s to the power 2k plus 1 over 2k plus 1 factorial. This is for that. And this is y is equal to this. And this is the solution to the differential equation up there. We call this solution the power solution. So this is the power solution to this differential equation. So this is the power solution to the differential equation. Okay, so I think that is all for now. Maybe you have to take your time to just expand what you have done here. But the most important thing is you should get your solution to be y is equal to summing from 0 to infinity, summing from n equal to 0 to infinity, and then you have a, n, then s to the power n. And then you try to get your recurrence relation, and then you expand, you substitute them into the main equation and get the general solution for your function. Any question? Please, any question? Hey, mini online. I'm online.
You're online, madam. No
That's you
question.
are in. You are online.
Please, you just take your time to read the last one. I don't know. Do you have the notes already? Have I given the note to you already?
No, madam.
Okay. So I will send the notes to the course rep. Or this person. Who is this person? You have who?
There, it's there. It's there, madam.
So this is the end of the ODE. I don't know if you have anything, any problem, anything that you want us to discuss, but I will share the slides with you. Do you have anything for me? Course rep, Peter, I'm done.
Doctor. Okay, doctor.
I'm done.
Thank you very much.
You're welcome. So please take your time and then go through what we've done, especially the third one, the lesson 3. I'll share everything with you. Gloria,
Madam.
I'm done.
All right, madam. It's well.
So we'll meet somewhere else, but please try and then understand what we have here.
Okay, madam.
I wish all of you the best, and we'll meet somewhere, maybe on your graduation day or another place.
By God's
So
grace. Thank you.
Yeah,
madam.
thank you too, and see you in person one day.
Madam.
We are grateful. Thank you.
Hello,
too.
madam.
Hello, Peter.
So this time around, we are not going to get the trial questions, the 40 trial questions that you said the other time.
Okay, so I'll talk to Dr. Anochi and see if he has some trial questions. So we'll try and get you some trial questions. But please keep on reminding me because I might forget.
All right, doctor.
Okay, thank you very much, and I wish you all the best.
Thank you,
Have
too.
a good
Thank
evening.
you.
Okay, bye-bye.
Thank you. Bye-bye.
Bye. You're such a nice person.